Hello and welcome to our final presentation for MIE 519 on the application of friction stir welding techniques in the automotive industry. We are Group 2. So first, for some background. There is an increasing demand for more fuel-efficient cars, and the way that car manufacturers have approached this problem is to use more lightweight materials. And several components of a car can benefit from this, such as the suspension arms or the engine brackets. And the basic operating principle, as seen on the image on the slide, is that some portions of a part may not need to hold as high of a load, so you're able to use more lightweight, weaker material. In this case, aluminum versus steel. Car manufacturers already utilize using different material strengths for the way a car crumples during a crash. So as you can see in that image, they might use higher strength steels in certain areas than others. And this is a great area for a lot of opportunities to reduce the weight of the car by using, for example, a high-grade aluminum instead of steel to make it lighter. One of the most common ways that metal components are joined in a car manufacturing setting is through fusion welding, and more specifically spot welding. So you can see those robot arms in the bottom right, which are extremely good at welding in these complex geometries. Um, but the thing is, fusion welding has to melt the parent material to work. And when joining dissimilar metals by fusion welding, this results in the formation of intermetallic compounds, which weaken the joint between the two dissimilar metals. Solid state welding is a method that is less often used in the automotive industry, uh, but the operating principle is that instead of melting the material, the metal is brought to a plasticized state, so it's closer to forge welding. And it's existed for many years through different methods, like rotary welding or friction stir welding. And now a bit more on intermetallic compounds. So intermetallic compounds are formed in the transitional zone due to chemical reactions between the different metals. They're notorious for weakening the weld joint. As you can see in the picture on the right, a crack is going straight through the IMC layer. The layer thicknesses of the IMCs in these dissimilar welded joints are usually on the micrometer scale too. Uh, the ability for different welding operations to join dissimilar metals is limited by the formation of these intermetallic compounds. So for fusion welding and solid state welding both have this issue. However, solid state welding has shown a lot more success in providing full strength joints of dissimilar metals, and this is because it results in joints with less porosity, less residual stress and distortion, and defects, and also because there's been studies showing that the less heat input there is, since it is a chemical reaction, the smaller that IMC zone will be. Now a bit more about friction stir welding, because this will be important later on. Like we previously discussed, friction stir welding is a solid state welding process, so it does not melt the material. It utilizes a rotating non-consumable tool that is usually made out of a very high strength durable material. The tool plunges into the material and traverses the joint of the two parts being joined, and most of the heat is generated by the shoulder while the pin stirs the plasticized material underneath. As you can imagine, it requires a very rigid setup because of the high forces involved with the process. Compared to other solid state methods, friction stir welding is not limited by size, making it more ideal for use in the automotive industry, so you can do a bit more complex geometries with it if you have the right setup. And it has shown in literature, as you can see in these images, a bit of success with joining dissimilar metals. However, this success is contingent on the choice of very finely tuned parameters to result in a successful joint, and these parameters would have to change based on the material thickness and type, and so there's still a lot of limitations in the process. Now that we've identified the different types of welding processes and their limitations in joining dissimilar metals, we can talk about the gap and how we can bridge that gap. So there is a need for a method of joining dissimilar metals that minimizes the size of the IMC layer to improve joint strength, and that is done in a cost-effective way for use in the automotive industry. And the way we're going to do this is by combining features from variations of friction stir welding processes. And we can design a process that is able to produce reliable dissimilar metal joints at increased speeds. One of the first ideas we found for improving the friction stir welding process was something patented by NASA called thermal stir welding, where you independently heat the two different metals to their own plasticized state, giving you a lot more control uh, over the heat input into the material. And they make claims of higher travel rates and more degrees of freedom, which are really good things to have in the automotive industry. The only problem is, while it was patented in 2011, we could not find a single paper in literature that even referenced thermal stir welding. So we need a more tested method for our design process. However, we can still take some ideas from thermal stir welding. Next up, laser-assisted friction stir welding. So there has been some um, studies in literature that have used a laser source as a supplementary heat source during the friction stir welding process that have shown to reduce the load on the tool, and as a result allow the tool to go faster in the material and allow you to weld faster. So in our design process, we need to address some critical limitations of the existing welding processes. First, we need to address the size of the intermetallic zone. We have to try and reduce that as much as possible for the integrity of the joint. And second, we need to increase the speed of the welding process to make it feasible in the automotive industry. So we chose to modify friction stir welding because it's an ideal process that can be scaled up to different geometries and sizes, which is useful in the automotive industry and has been modified a lot in literature. So there's a lot of information and data we can take from it. For our design, we've combined concepts from thermal stir welding and laser-assisted friction stir welding. And so we propose a modified version of the conventional friction stir welding process, which utilizes a supplemental heat source in the form of a laser for each metal, allowing them to be heated independently. This will allow the operator great control over the heat input into the joint to reduce the formation of the intermetallic compounds. We also plan on using research from literature to optimize process parameters specifically for dissimilar metal joining. To test the concept, we came up with some numbers for the parameters based on data we found from similar experiments in literature. And the potential setup is for performing a butt joint weld between 1 mm thick aluminum and steel sheets. So there are 6 main parameters that can be altered in the process. The tool material is the same as the one used in conventional friction stir welding, so a high strength material, which we've chosen as high carbon, high chromium tool steel. And then if you notice, a low tool rotational speed of 500 RPM, since the heat is being supplemented from the lasers, but also because literature has shown that lower RPMs result in a smaller intermetallic compound layer. Tool travel speeds up to 1500 millimeters per minute, which have been suggested by studies looking at laser-assisted friction stir welding. And finally, laser power, which we've seen in the range of 1 to 3 kilowatts in literature, which would be controlled by the temperature you would desire in the joint. So improvements over conventional friction stir welding, there's lower downwards axial force, so 33% less plunging force required in a study that looked at laser-assisted friction stir welding. There's a greatly improved welding speed, so up to 1,500 millimeters per minute, versus other studies which use conventional friction stir welding range from 20 to 100 millimeters per minute, which is much lower. And just in general, being able to control the heat input into the material gives improved material flow during the welding and better better mechanical properties while reducing the internal stresses. So some limitations, and there are pretty major limitations. So first is that by adding lasers, we are limiting the geometry and the joint types that you're able to make with the friction stir welding, just because there needs to be a line of sight with the uh, laser, so we lose some of that flexibility of friction stir welding. Second, lasers are expensive components, so whatever money you save by being able to have higher throughput because you have higher weld travel speeds, you have to compare that to the cost of maintaining those lasers. And finally, that the entire process is still extremely sensitive to the choice of parameters. So if you were to change the material type, the thickness, or the geometry, you have to change all of these parameters again. So in a automotive industry where if you're going to change the process, you have to go ahead and do this testing again and make sure that your process is as working as it should, which is time consuming. To summarize, the formation of intermetallic compounds is the largest challenge for current welding techniques to join dissimilar metals. And the IMC layer size can be minimized by controlling the amount of heat input to the weld. And we propose doing this by adding a supplemental heat source through the use of lasers. At the same time, the additional heat source allows for improved travel speeds and tool life due to the lower forces involved, which makes the process more feasible for use in the automobile industry. In the future, the design concept through a prototype would have to be tested with the parameters we suggested, and then the resulting IMC zone size will have to be measured and compared to other values in literature.